Again, welcome to Calculus. In these lectures, we will start with a basic concept, which will be almost a pre-calculus, or I would say an algebra. So this is again our first course in the calculus class, which is Unit 1, lecture number 1. So we are starting with pre-calculus or college algebra. So our main objective in these lectures is to identify different types of numbers. Also, we are going to determine if given numbers are greater than, less than, or equal to other given numbers. Also, we are going to interpret set builder notation and also determine absolute values. So we start with the first example type of numbers. So we have a power number here, and when we look at the power number, it's 3.14159,265,358,979, and it keep going. So the decimal number is infinity. So this means again, a power number is an irrational number. So a power number is an irrational number. The decimal number is infinity. And here we say written as a decimal number, it is an infinity non-repeating decimal number. So it's an irrational number. And normally the 3 period that we wrote at the end of the last decimal digit number indicate the decimal is not terminated, so it's infinity. Also, since there's no block of digits, which is shown as repeating, we can infer there is no repeating block, and thus infer is that power is an irrational number. The goal here again is that the power number, the decimal value is non-repeating infinity number. So it's again a rational number. And second, we have 1 by 7. 1 divided 7 by 7 will give us 0.14285714287. Again, the same thing, we have repeating infinity digits. So solution of 17 is a rational number because we can also write 17 as 0.142857, where the bar is used to indicating the repeating pattern of digits. So we can see the reason why this is a rational number, because after we reach 7, 0.142857, we are repeating the decimal number 142857. So the next decimal number will be again 142857. In the power number, the decimal numbers are non-repeating. They are non-repeating decimal numbers, infinity. 17 is a repeating infinity decimal numbers also. So it's rational. So again, 17 is a rational number. Now we have 3/4. 3/4 gives us 0.75, which means, again, we end, the digit end at 2, 0.75. It's not infinity. So it's a rational number. So if we have a decimal number and it's non-repeating infinity decimal numbers, then it's irrational numbers as the power number. 17, we have repeating infinity, but since it's repeating decimal number infinity, it's rational. Now 3/4 here, we have 0.75, which means it ends. It's finite. So this means it's also a rational number. The repeating number will be 0. So we are going to repeat 0, 0 over and over again. So it's a rational number. Also, we have negative 2/3, which gives us negative 0.66666. So again, it's a rational number because we are repeating the decimal number 66 all over. It's like 3/4 will be 0.750000. So it's repeating. So again, it's a rational number. Now we have a square root of 25, which gives us a 5. So the solution also will be a rational number. A whole number is always a rational number. Now we have alpha equal to 1.020030. Again, when we look at this value, we can say that there's a repetition. So here we say alpha is not a rational, there's no repetition. We can see that 1.02003304, and we keep going. So we are not repeating the same decimal. Next, I'm going to have 6 zeros with 7 zeros. Then we keep going. So alpha is not a rational number. The size of the blocks is consecutive zero growth and never repeats. The key word again is not repeating. Even we have infinity decimal numbers, they are not repeating. So here we go through the properties of addition and multiplication. So our first objective, we cover what is a rational number, what is irrational number. Now the next objective is to know how to do, again, a basic addition and multiplication. So properties of addition and multiplication. So for addition, if I have A plus B, is the same as B plus A. And this is, again, commutative property. In multiplication, it means A times B is the same as B times A also. With associative property, if I have A plus parenthesis B plus C, is the same as taking the C out of the parenthesis and putting A. So A plus B parenthesis plus C is the same. With multiplication, also the same thing. A times parenthesis B times C, close parenthesis, equal to open parenthesis A times B, close parenthesis, times C. This is called the associative, again, property of both addition and multiplication. Identity is, if I have A plus 0, I'll get to A. And if I have A times 1, I'll also get A. So that's the identity. Identity of multiplication, you multiply the value by 1 to get the same value. With addition, you add the value to 0 and you get the same value. Then we also have the inverse properties, which is A plus negative A will give me 0. With addition, we are going to divide. So A divided by A will give me 1. Or A multiplied by 1 over A will give me 1. We also have the distributive property for multiplication over addition. So if I have A, parenthesis, B plus C, I can open the, always we assume parenthesis is multiplication. So we can open the parenthesis and have A times B plus A times C, which is called the distributive property. So we have a second example, and this second example is about number line. And the goal is that we have a list of values here. We want to know which one are lesser and which one are greater. So it's more or less like we are going to sort the values here in increasing order. The smallest values will come first, the largest value last. So here we're going to use every dot and estimate the placement of the points that are not integers also. So this will be our solution: negative 25 square root, negative 3, negative 1.5. So we know negative 3 is less than negative 1.5, and 0 is greater than any negative value. Then we have 3/4, which will give us 0.75. Square root of 3 will give us 1 point something, so it's bigger. Power is 3.142 and 4. So we place the values in increasing order from the lowest value of negative square root of 25 to 4. So next we want to know the symbols for orders. We know the left arrow means less than, the right arrow means greater than, the left arrow with a bar means less than or equal to. So the bar means equal. Or the right arrow with the bar means greater than or equal to. So here we are going to arrange the following numbers in order from the smallest to largest using the most appropriate of the four symbols. Either greater, less, greater than or equal, less than equal. So we have to arrange. So the smallest value will be negative 20. So negative 20 is less than negative 17, and negative 17 is less than negative 1.7. Negative 1.7 is less than 0, and 0 is less than 1.7, and 1.7 is less than 20 divided by 3. And 20 divided by 3 is less than or equal to 40 divided by 6. So actually they are equal. So that's why we have less than or equal. Then 40 divided by 6 is less than 17, and 17 is less than 20. The next is set builder notation. So here they say we should grab the set of real numbers. So when we write x, given x is less than 3, it means we are going to have x values from any value less up to 2, not 3. So to grab this, we are going to put a circle with a hole, a point with a hole to the left, because we know all the values to the left, they are less than 3. And when we put a point with an hole, it means the value will not reach 3. So we say the open circle indicates that 3 is not included in the set. So here the set of real numbers from negative infinity to 2, or 2.9999, 3 is not included. Next, they say we should graph s greater than or equal to negative 1.5. So this is greater than or equal. And since we have equal sign, it means negative 1.5 also is included. So to grab this, we are going to use a circle with no hole. It's again. So this no hole means including negative 1.5. Since it's greater, it will go to the right. So it will go all the way to positive infinity. So if the number is included, we use the circle with no hole. And if it's not included, then the circle with hole. So here we say the closed circle indicate that negative 1.5 is included in the set. Next, we go through what is absolute value. So we know absolute value, the rule said whether it's positive or negative, the answer always will be positive. So absolute value of A can represent ordinary value of positive A or negative A, because absolute value of negative A is A, absolute value of A is A also. So we have some examples here. We should find the absolute values of each of the numbers given. So we have negative 10 will be positive 10. So the absolute value of negative 10 will be positive 10. Now absolute value of negative 2.3 will be positive 2.3 also. And absolute value of 4.5 will be 4.5. And absolute value of 0 will be 0. So next, we will look at example for absolute value equation. So here, what real numbers satisfy the following equation? We have an absolute x equal to 4. So if we have 4, then the answer is 4. Absolute 4 is 4. Same thing if we have negative 4, it still will give us 4. So this means s can be positive 4, and also it can be negative 4. So negative 4 will give me 4, positive 4 so will give me 4. So what real numbers satisfy the following equation? X equal to negative 1.7. So it's the same as the previous example. We are going to have negative 1.7. Yes, so the equation has no solution. Why? Because anytime we have a absolute value, the answer should be positive. So negative one, absolute value of negative 1.7 will be positive 1.7. Absolute value of 1.7 will be 1.7. So here we say the equation has no solution because absolute value of any real number is always non-negative. So this will be the conclusion of our first lectures. Again, this is a calculus course, and we are starting from lecture number 1, which is more or less pre-calculus, or I would say college algebra. So again, see you in the second lectures. Thank you. Bye.